Hello everyone. So today we're going to start on 6.2. So in 6.2 what we're going to try to do is build up on what we have learned in 6.1, mainly about chain rule, and try to now generalize it into functions that have several independent and as well as dependent variables. So before we get started, let's do a quick recap. So in BC calculus, what you learn is that if you have a function f that maps from R to R, and a function g that map from R to R, then we can define h that map from R to R such that h of x is equal to g of f of x. So in this scenario, remember the general idea is the following. Let's say we start with x, then the function f would generate a value u, and then u go through function g would give you y, and then the function h would directly take you from x to y. So in this scenario, we have, let's say f of x is equal to u, g of u is equal to y, therefore h of x would equal to g of f of x, which is equal to y. So important to make sure you understand is that in this scenario, the composition basically allows us to change from x to u to y, and then the composition, the function h is basically directly talk about what's between x and y together and bypass u in a way. In here, the chain rule dictates the following. So this is the chain rule from BC calculus, which dictates the following. H prime of x is equal to g prime of f of x, multiplied by f prime of x. So that's the chain rule that you learn from BC calculus. And important to remember is that's for derivative of a composition that has two single variable real value function. Okay. Now in 6.1, we learn a little bit different chain rule. We learned the following. Let's see we have f that map from R to Rn. So remember, this represents a curve in Rn. And let's say we have a function g that maps from Rn to R. And that is an n-dimensional surface in Rn plus 1. Then we can form the composition h this way. H would map from R to R also. Now, why is that? Because in this case, well, let me finish this first, such that h of t is equal to g of f of t. So how does this work in this scenario? Well, first of all, in this scenario, the first thing you need to notice is the following. Is that this function h basically take from R to R because it starts from R and go through the function f to generate something in Rn, and then the Rn just so happen can plug into function g to go back into R, and then the function h directly go from input to output. Or another way to look at it is the following. It starts with the input t, it changed by f to some position vector, vector x for a curve, and then the position vector x go through g, gives some kind of output, and the function h directly link t and y together. It is important to think in terms of how one variable affects another one, because essentially when we start talking about derivative, or in this case actually more likely we'll talk about what we call partial derivative, eventually it's always talk about how one independent variable changes one dependent variable. So therefore, always things kind of in terms of like what is the input variable, what's the output variable, and then you'll be able to understand what the derivative is designed to do. It's basically designed to talk about how the independent variable changes the dependent variable. And it's no different than the derivative that you learn in BC calculus. The only difference is there are multiple independent variable and multiple dependent variable now in one single function. And what's the chain rule in this case? So 6.1 chain rule basically states the following. So 6.1 chain rule say that if you take the derivative of h prime of t, that's basically equal to gradient of g at f of t dot product f prime of t. So that's 6.1 chain rule. So now what we're going to try to do now is to generalize this concept so that we can talk about what if we have multiple independent variable and multiple dependent variable. Now, one of the interesting thing about the theorem 6.1 and the BC calculus chain rule is the fact that both of the composition result in one single independent variable and one single dependent variable. In the case from BC calculus, you are calibrating x and y together with an intermediate variable u, the gap between the function f and function g. In 6.1, you are also talking about a single independent variable with a single dependent variable. But in this case, the single independent variable is t, and then the dependent variable is y, and they have this intermediate variables, vector x involved. And also one thing I also want to point out is that even though in this scenario h of t equal to f of g, g of f of t give out one single variable as one single input, the graph of this function h actually is in Rn plus 1. And the reason why that is the case is because the following. Important to note this. The graph of h of t is actually a curve in Rn plus 1 on the surface of the function g. The reason why is because when we graph this, we actually graph f of t comma h of t. And how does that work out? F of t, or maybe I write this, is vector x, and then h of t is y. And since vector x is in Rn, h is in R1, therefore together become Rn plus 1. Okay? So important to notice that that's slightly different because when you evaluate h, you actually evaluate two different things. When you evaluate h of t, the t would evaluate f of t first, which give a vector x, and then give a g of f of t, which give a y value. And then both of those combine to draw the graph. Now, so what happened now in 6.2? In 6.2, we want to deal with the following. What if we have a multivariable function f and a multivariable function g that is vector value? Okay? So meaning what happened if you have f and g both are multivariable and vector value? Can we still form the composition? Well, yes, we can, as long as the following is true. Okay? Let's say we're given a function f that map from Rn to Rp. And we're going to define this function f of vector x equal to some vector u. In order for the composition to work, what must be true is this, is that the image of the inside function, which in this case f, must be the same dimension as the input, the domain of the outside function. if that is not the case, then you don't have the proper vector to plug into the outside function for the composition to work. So in this scenario right here, we have to define G to have to start from RP so that it work with the output of F and map into Rm. So in this case, we will say that G takes in vector U and give out vector Y. So it's extremely important that that is the case, that the output of the function f have to be in a dimension that matches the domain of G. Otherwise, the composition wouldn't work. So how does the composition work? In this state, the composition would work from this. It would take vector x through the function f to give me vector u, and vector u through the function G would give me vector y. And in other words, it would take something in Rn through function f to give you something in Rp, and just so happened something in Rp can be plugged into G to get something in Rm. Now, of course, in here we go define our composition H to map from Rn to Rm. And composition H will be H of vector x equal to G of f of vector x. And so what does the function H do? Function H directly connect vector x to vector y, bypassing vector u. Now, remember, when I say that, that would imply that we actually form the function h instead of looking at it as some kind of composition. Okay, but if you're unable to combine the two functions together for whatever reason, then even though you define the single function that relate x and y together, but you still have to functionally treat them as a composition. Okay, and remember, I guess I'll write this again. Remember the difference between these two examples. You know, if I have x of x equal to x squared and g of x equal to x to the third, then I can say h of x is g of f of x, and that would just equal to x to the 6. So I actually formed the function h, and I can look at function h as a single function, which is just x to the 6. As compared to something like, in this case, f of x equal to maybe sine x, and then g of x is x squared. Then in this case, h of x, you know, can be written into a single function, sine square of x, but then when you evaluate it functionally, you still have to evaluate first sine x, then square. Okay, which is different than you can just say x to the 6, and that's completely done without worrying about like what happened to x to the third and x to the second. So that's functionally different between them, even though it's a minor difference, but it's still important to note the difference because it dictates how you take the derivative of it. If you actually combine to one single function, like in the top case where you combine to x to the 6, you can just take the derivative directly. But if you have to treat it as two separate things like sine x, sine square x, then you have to apply chain rule. So that's the difference between the two. So now comes the big question. What is the definition of chain rule in this case? So for lack of a better description, I'm going to say 6.2 chain rule, which will be different than our 6.1 chain rule, of course. So what's the definition of 6.2 chain rule? Actually pretty simple. If you have, if you're given f map from Rn to Rp and G map from Rp to Rm, then we can define H, which map from Rn to Rm, such that H of vector x is equal to g of f of vector x, and then the chain rule would dictate that h prime of x the derivative h prime of vector x would equal to g prime of f of vector x multiplied by f prime of x. Now, notice that that looks strangely like the chain rule that we wrote right here. Except the only one major difference is that I draw vectors over the x. Okay? But it's actually extremely different because of the following. In this scenario right here, because both g and f are vector values several variable function, their derivative is now defined to be derivative matrix. So make sure you pay attention to that note. G prime and f prime are both derivative matrix, which is the reason, or matrices, which is the reason why there is a lack of dot product between them, because in this case here we are talking about matrix multiplication involved. And matrix multiplication doesn't require symbols because it's kind of like regular multiplication. But it does require dimension to be consistent for the multiplication to be defined. And it does, in this case, if you think about it, the derivative G prime should be a matrix that's M by P. While the derivative matrix for F, which is F prime, is a derivative matrix P by N, and therefore they result in a product that is M by N, which is exactly what the derivative matrix of H is supposed to be. Now, because of the fact that we are using matrix multiplication, it's extremely important that you do not do this. Is to write it in the wrong order, which is to write it this way. Okay, this is wrong. Why is it wrong? Because the matrix cannot be multiplied together this way. Okay, because in this scenario, you basically have a P by N matrix and try to attempt to multiply by M by P matrix, and that multiplication is invalid. And therefore, your chain rule is actually incorrect when you write it this way. Now, with the chain rule from BC Calculus, it really doesn't matter. Okay, but because of the chain rule in 6.2 require matrix multiplication, you have to pay attention to dimension. If you don't do that, you wind up writing something that cannot be done. And if you do that, I will have no choice but to take points off. Now, show you some basic idea of how this works. Because this type of question require multiplication between matrices, I will try to keep the matrices to be smaller dimensions so that as not to burden you with a lot of basic arithmetic. And most likely in tomorrow's video, we will talk about what if we only want one thing within this derivative composition. Maybe we don't need to know the entire matrix. Is there some way to generate only one of them? And that's what we go also focus on too. But we'll get to that. So now let's start with some very simple example first. How about we have this? Let's say given f of uv is equal to u squared plus v squared, u squared minus v squared, and that equal to xy. And then we have g of xy, which is equal to xy x plus y. Okay, and the output here could be something, but I just want to link the f to the g, so I call f, the output is x and y. If you have to, I guess I can say, how about we call this zw? Okay, just kind of be consistent. How about I ask you to find the following? Let's start with the first one. How about we find g composition f prime of x, and then of xy actually, of uv actually, and then evaluate it at, let's say, 2, 1. So we can definitely define h of uv to be equal to g composition f of uv, which basically means g of f of uv. Now, here's something important that I want to make sure you understand. What is the output of h then? Well, output of h, give me fw, zw. That's what the output of h is, because output of h matches the output of g, and the input of h matches the input of f. And while the output of f and the input of g are what's happening in the middle. Okay, so therefore, if you think about the way they work, is that the vector uv would change by f into the vector xy, and then change by the function g into the vector zw. They're all in R2, while the function h directly linked between uv and zw. So in this case, we have f map from R2 to R2, g also map from R2 to R2. In this case, h also map from R2 to R2. Now, these are all things that are important. They might not play a part in the function of the question itself, but it's important for you to understand what you try to do and make sense of what you try to do. So please make sure you pay attention there and try to understand that, because if you don't, you are basically missing out on a lot of things, and that's going to screw you up eventually. So how do I form the derivative h prime of uv? Well, simple. Based on the chain rule, that's g prime of f of uv multiplied by f prime of uv. And no, you don't put a dot between them, because remember, it's matrix multiplication. So now it's just a matter of go for it and find these two derivatives and then multiply them together. So let's start with the easy one. What is f prime of uv? So if I'm looking at this correctly, f is u squared plus v squared and u squared minus v squared. So f prime of uv is a 2 by 2 derivative matrix. It would be 2u, 2v, 2u, negative 2v. And yes, you do need to be able to take partial derivative as quickly as I'm showing you right now, because otherwise you go take too long for you to complete a problem, which, like in this case, require you to do about like 8 to 12 partial derivative. And if you take you too long to do that, you're not going to be able to have time to finish the problem that you have to do on your tests. We can definitely do g prime too. Well, g prime is of xy. So a little different. So g prime of xy would actually be, let's see, yx, and then 1, 1. So that's easy. But remember, we do need g prime of f of uv. So what would that be? So g prime of f of uv would basically mean g prime of u squared plus v squared and u squared minus v squared. So therefore, that becomes this matrix. U squared minus v squared, u squared plus v squared, 1, 1. I do need g prime to be expressed in uv, because h prime is only in terms of u and v. So therefore, it really shouldn't have an x or y in it. So now I'm ready to form my derivative. My derivative h prime of uv would equal to g prime u squared minus v squared, u squared plus v squared, 1, 1, multiplied by 2u, 2v, 2v, negative 2v. You will be marked incorrect if you write these two things backward. First of all, the reason is because, yes, it is true that writing them backwards still make the multiplication valid. That is true. But the problem is matrix multiplication is not commutative. There's no guarantee that if you multiply these two matrices backward, even if it defined, would give the same answer. So therefore, that would have to be marked incorrect. So please make sure you understand that and pay attention to that. So now I'm going to multiply them out. So if I multiply them out, I get basically 2u times this, which is 2u to the third minus 2uv squared. And then 2u times the u squared plus v squared, so become plus 2u to the third plus 2uv squared. And the bottom one is just 1 times 2u, so become 2u plus 2u, so that's easy. Look like I'm going to need a little bit of room. Okay, we'll try to squeeze in here. Okay, now I'm going to do u squared minus v squared, u squared plus v squared times 2v negative 2v. So therefore that would become 2 u squared v minus 2v to the third, and then minus 2u squared v minus 2v to the third. And then here I would have 2v minus 2v. So it looked massive, but I noticed a lot of you don't do this, and you have to, which I understand from BC Calculus. Mr. Ambrose probably asked you not to simplify things because the AP exam does not require you to do that. But it is definitely something good to get habit of, is to simplify your expression so that it make the math easier to do. So here, definitely don't write this in the answer, because you notice that minus 2uv squared and plus 2uv squared cancel out. And 2u squared v minus 2u squared v, they also cancel out. No reason to write them when they cancel them out. So therefore, it seems to me that this is probably the answer that I'm looking for. Is 2u to the third plus 2u to the third, which that's 4u to the third. So please don't write 2u to the third plus 2u to the third. 4u to the third. And then negative 4v to the third. 2u plus 2u is 4u. And 2v minus 2v is 0. And if I evaluate this at 2, 1, notice I can directly plug it in, because 2 in this case represent u, v represent 1. How do I know that? Because it asks me to evaluate g of f prime of uv, so the input have to be uv, so therefore the value that I'm given has to be for uv. And if it's not for uv, I will have to specify that so that you don't get confused. So in this case, seems to me that would be 2 times 4 times 2 to the third, which is 8, so that's 32. Negative 4 times 1 to the third, which is 1, so become negative 4. 4 times 2 is 8. And this one is 0, of course. So that's my answer, and that's my answers. Now, look like I probably have time to just do one more example with you, and that will probably be the end of today. So how about we have this? Let's say given f of t is equal to t plus 1 e to t, and let's say g of uv is equal to u squared plus v to the third e to the uv. And I'm going to ask you to go ahead and find h prime of t, which is basically g of f of t. Oh wait, actually maybe I just write it this way, just to be clear. Let h of t equal to g of f of t, find h prime of t. So in this scenario right here, we are treating the output of the function f to be uv. So here that means that f of t is t plus 1 e to t, which is equal to uv. And then g of uv would equal to u squared plus v to the third, and e to the uv. Maybe I'll call that xy in this case. So therefore, our function h of t would directly give us the vector xy, just like before. T would go through f to form the vector uv, and then that go through g to form the maybe I'll write it this way, uv into xy, and then h directly go between t and xy. Now, at this point, some of you might be thinking, can I just form h and then take the derivative? Yes, you can. The only problem is that the function h might be extremely complicated with both of them kind of plugging into each other, but in some cases, it might be easy to do. Now, however, with that being said, it doesn't help you when we talk about how to find a specific derivative. Okay, so therefore it doesn't help you on the next one we're going to talk about. Now, I do know that it's past 30 minutes, so let's quickly do this. So I'm going to go ahead and start with h of t first, f of t first, f prime of t first, which is easy. That's 1 e to t. G prime of uv is actually equal to 2u 3v squared, and then you know what? Actually, I'm going to change this. I'm going to change this UV here to just UV just to make the problem simpler, because I don't have time to go through the whole thing. So I'm going to make this that. So that's just become VU. And so if I now plug it in f of t, what I have will be the following. 2u would be just 2t plus 2. 3e squared would be just 3 v is e to t, so 3e to 2t. And then here will be just e to t and t plus 1. So now I can form my composition derivative, h prime of t, which is basically equal to 2t plus 2, 3e to 2t, e to the t, t plus 1, multiplied by 1 e to t. Notice that the function f prime has to be written vertically, otherwise the multiplication doesn't make sense. And so if I do that, that will be 2t plus 2 plus 3e to 2t times e to t, which is 3e to 3t. And then the bottom will be e to t plus t plus 1 e to t. Note that the bottom actually can be factored. So if you factor it correctly, you actually have the following. 3e to 3t plus 2t plus 2. And kind of line them up in the right order. And then the bottom, if I factor out e to t, I actually get t plus 1, which is t plus 2 e to t. So that becomes my derivative. All right. Unfortunately, my time ran out, so I think we have to stop right here for today. We're going to continue some more in tomorrow's video. All right. Talk to you guys later. Bye-bye.